to mole conversions. Mole to mole conversions are only the direct comparable conversions that you can do from either one element to a different element, from compounds, from anything. So there's no direct conversions from grams to grams or particles to particles. You always have to go through moles. Moles are the only directly comparable units for elements in the metric system. And you use things called mole ratios. Now, I want to make sure that people understand that when you're looking at stoichiometry, they're just molar conversions between a balanced equation, and sometimes you do balanced compounds. We start with balanced compounds first. So please remember, you balance compounds with subscripts. So in compounds, the subscripts show moles, whereas you balanced equations with coefficients, and therefore the number in front of a compound says how many moles of a total compound you have. So remember, compounds, subscripts, equations, coefficients. The two C's should never touch. Okay, and they're the only direct ratio or the only direct item that can be directly compared is moles to moles. And you write your mole ratio, mole A over mole B or mole B over mole A. A lot of people ask, when I'm just giving you or outlining the potential of ratios, does it matter what goes on top or bottom? And the answer is no, it doesn't, as long as I can see that you've represented the different potentials. What does matter is when you're doing your molar conversion, that you're following the proper dimensional analysis formatting, which I'm going to show you. Okay, so now let's talk about mole ratios. And specifically, how to break down a compound. So I'm going to write a sample compound. Na2O. So we're going to break down the compound, and when you're breaking down a compound, look at it. Think to yourself, is there a coefficient? If there isn't a coefficient, you assume 1. And when you're doing molar ratios in a compound, you always assume 1 of the compound. So we have 1 mole of Na2O. But you have to break it down to the separate pieces. And if you're not exactly sure how to do that, a great piece of advice is to break it into words. Sodium oxide. You have 2 words, so there's 2 pieces that go into it. So I have Na2, that 2 is a subscript. Remember, the subscript's that little number that goes below, and that 2 goes with that Na. So that's 2 moles of sodium. And remember, sodium's in column 1, so it's Na1 plus. And then we have O, we've written it 1 time. There's no subscript, so we can assume 1 mole O. Remember, oxygen's in column 16, and so that's O2 minus. And the most correct way is to write the ions fully, because you're breaking apart sodium oxide into sodium ions and oxygen ions. So now you have to do your mole ratios, and an easy thing is if you've already built or pulled the pieces apart, and you don't always have to do this, it's easy to see what goes together. You have 1 compound with 2 pieces, so each piece should go to the compound. So you should have 2 ratios with a compound in them, and then the 2 pieces have to go together. So we have 1 mole sodium oxide. And then you can do the line right through. I like to skip over my subscripts so I can see my subscripts. And you think of a ratio as this. For every 1 mole sodium oxide, I have 2 moles of sodium. And also for every 1 mole sodium oxide, I have 1 mole of oxide. And also for every 1 mole of oxide, I end up with 2 moles of sodium. And it's important to note that these are like the pieces of a recipe. So for sodium oxide, to make 1 sodium oxide, it's 2 moles of sodium to 1 mole oxygen. And your mole ratios allow you to manipulate the basic recipe so that you know how much of everything you need given more than one of everything. Okay, so let's do the mole ratios of calcium chloride. Okay, so remember before we do mole ratios, and we want to do the mole ratios of calcium chloride, we do want to break it down into a balanced equation. And remember, there are 2 basic ways of balancing equations, either the LCM method or the crisscross method. So for calcium chloride, let's do the crisscross method. So you have calcium, which you can pull down into its ion. So remember, you can look at the periodic table and you find calcium. The element symbol for calcium is Ca. And remember, calcium's in column 2, which is an alkali earth metal, and those have charges of 2+. Then you have chloride, and remember, you go after the root. The root is chlor, and so the symbol for chlor is Cl. Cl is in chlorine, which is in column 17, which is a charge of 1-. Now remember for the crisscross method that the number of this charge becomes the subscript of the opposite item. So this 2 becomes the subscript of this chlorine, and this 1 becomes a subscript of this calcium. So I have Ca, and I'm going to write it 1 time because I have a subscript of 1, and writing it 1 time meets the need of that subscript, so I don't have to write the subscript of 1. And then I have Cl with a subscript of 2, and that gives me a balanced calcium chloride. Okay, so now let's break it down. I have 1 mole of the entire compound, so I have 1 mole calcium chloride. Then I have to break that compound down. It's easy to say, except for calcium chloride, but look at the names. I have calcium, which goes with Ca. I have chloride, which goes with Cl. So I know I have to break it down to at least 2 more things. So I have 1 mole of calcium. As I said before, you wrote it 1 time, no subscripts. That shows 1 mole. And don't forget to put your ions. So that's Ca2+. And then I have 2 moles of chlorine. And from this information, I can make my mole ratios. Perfect. So one potential mole ratio would be 1 mole Ca2+ to 1 mole Cl1-. Perfect. Remember, you're pulling the information right from here, or you can be looking at the compound and pulling this information too. If you feel that you're too advanced for this step, both are acceptable ways of pulling the moles. Another mole ratio you could write is 1 mole CaCl2 for every 1 mole Ca2 plus. And remember, for writing down the potentials, it doesn't matter which one's on top or bottom, because it'll be very clear which one needs to be on top or bottom for the solving, because we'll be using dimensional analysis. So what is the last mole ratio? So then you could do 1 mole calcium chloride to 2 moles of chlorine. A nice, easy way of checking if you have all of your mole ratios done is you have calcium and chloride. So have you done calcium to calcium chloride, chloride to calcium chloride, and then calcium to chloride? Okay, balance and do the mole ratios for sodium nitrate. So remember, an 8 in an ite is going to be a polyatomic with oxygen. And if you have more than an 8 or an ite, or if you have more than one of a polyatomic, you need parentheses. So remember, sodium is in column 1, so it's Na1 plus. Nitrate is a polyatomic that you had to memorize, and it's NO3. 1 minus is a 1-to-1. So if you crisscross it, still a 1-to-1. So it ends up being Na NO3. Okay, so we did the math. We have 1 mole sodium nitrate. We have 1 mole NaNO3. Also pulling from the equation, we have 1 mole sodium. And remember, you should put it in ion form, so it's Na1 plus. And then a common mistake is to say that you have 3 moles of nitrate, because students see that 3 there and they are reading it correctly. Subscripts tell you how many moles you have, but you have to remember that nitrate's a polyatomic, so it balanced itself as NO3. So especially with polyatomics, if it's not in parentheses, assume 1. With polyatomics, especially with those compounds like nitrate, nitrite, acetate, ammonium, if you need more than 1 of them, they'll be shown in a parenthesis, and then the subscript outside of the parenthesis tells you how many moles of that compound you need. So seeing nitrate's not in parentheses, you have 1 mole NO3. So one of the mole ratios we have is 1 mole NaNO3 to 1 mole Na1 plus. Okay, what's another ratio we could have? Another ratio we could have would be 1 mole sodium nitrate to 1 mole of nitrate. Okay, what is another ratio we could do? Okay, and then the last one we could do would be 1 mole of nitrate to 1 mole of sodium. Okay, it's time for you to try one by yourselves. Okay, try this one by yourself. Problem solver 1. What are the mole ratios of potassium oxide? Okay, so for potassium oxide, you have to balance it first. Remember, potassium is in row 1, so it's K1 plus. Oxide is in row 16, so it's O2 minus. So by doing the crisscross, you get K2 and then O. Perfect. And then the next step is to break it down. So you have 1 mole potassium oxide, 2 moles of potassium. Don't forget your ions, 1 plus, and then you have 1 mole oxide. And then from our moles, our breakdown, or from our balance equation, you can go ahead and pull your mole ratios. We have 1 mole potassium oxide for every 2 moles of potassium. You have 1 mole of potassium oxide for every 1 mole of oxide. And you have 1 mole of oxide for every 1 mole of, for every 2 moles of potassium. I'm sorry, I misread that. Okay, let's try another problem solver. What are the mole ratios of iron 3 carbonate? Okay, so for iron 3 carbonate, I'm still going to walk you through again how to balance it using the LCM method, because I just want to do a little refresher, because a lot for moles and stoichiometry are balancing compounds. So remember, iron 3, those Roman numerals show you the charge of the iron, and that's for a transition metal. So for iron 3, it's Fe3 plus. Carbonate is a polyatomic, and it's CO3 2 minus. We did the crisscross method before, so I'm going to show you the LCM method. So remember, you have to do LCM, and that's the lowest common multiple between 3 and 2, and that's the lowest number that they both go into as a whole number, and that's going to be 6. And then you can make your LCM table, which is going to be your element over here, or compound. Then the next one's going to be your charge number. And the next one's going to be your subscript. And then finally, it's going to be your LCM. I'm going to color code these so you can see how the crisscross would work. So for iron, sorry, I'm going to do carbonate first because I have the green in my hand. My charge number is 2. Don't worry about whether it's positive or negative because your subscripts have to be positive. For iron, it's Fe, and our charge number is 3. Our LCM is 6 for each. So then you ask yourself, remember your charge times your subscript has to equal your LCM. So 3 times what equals 6? That's going to be 2. And that's how the crisscross works. Then for carbonate, 2 times what equals 6? That's 3. That's how the crisscross works. And please remember, the really cool thing about these subscripts over here for the LCM, these are outlining your moles. There's a nice visual on your moles if you're a more visual person. So now you have to write your balanced compound. So it's Fe2. And then remember, CO3 is a compound in a polyatomic with more than 1, so you put it in parentheses. CO3, 3. So I'm going to walk you through the answers. So the first thing is a compound, there's no coefficient, so you have 1 mole, Fe2. CO3, 3. Then we have a 2 down here attached to the iron from our subscript, which tells me I have 2 mole Fe3. 3 plus, and CO3 is in parentheses, which means I know I have more than one of them, and outside of that parentheses, I have a 3, so I have 3 moles of carbonate. So I have 3 mole CO3 2 minus. Now using this information, I go ahead and build my mole ratios. So for every 1 mole iron 3 carbonate, I do have 2 moles of iron. And for every 1 mole iron 3 carbonate, I do have 3 moles of carbonate. And for every 2 moles of iron, I do have 3 moles of carbonate. Remember the ratios, you always have to remember your lines. Okay, so now let's talk about how to complete the conversion from moles to moles. Mole to mole conversions are a dimensional analysis conversion. So you're going to place the amount of mole A given on the left. Then for your conversion factor, you're going to put mole B on top, mole A on the bottom using a mole ratio, and then you're going to solve. Okay, let's talk about mole ratio setup, because there's a very specific way, and the really cool thing about mole ratios, it is incredibly formulaic. So mole A is always going to be what you're given. So over on the left side, you're going to write mole A given. Please note, don't ever put what you're given in your mole ratios. Your mole ratios are always to one of the compound. You have to be able to say, here's the moles for my compound versus here's the moles that I was given. So mole A given always goes outside of your mole ratio. Then here is your mole ratio. This is going to be your mole ratio conversion factor. And mole A is going to be on the bottom. Because remember, mole A has to be able to cancel out, leaving mole B, and mole B is what we call what we need on top. And then you end up being able to solve for mole B. This is the setup that you should be using for all your mole to mole conversions. Okay, let's do a sample problem. Given the compound calcium carbonate, how many moles of carbonate are present if there are 5 moles of calcium ions provided? So let's talk about how to do that problem. So the cool thing about that problem is you were already given a balanced compound. You were given the compound CaCO3. So calcium carbonate. So remember, when in doubt, to name it, or you can highlight it, especially your polyatomics. So CO3 is a polyatomic. So remember, there's no parentheses, so there's just one of them. And that's the important thing when looking at the different subscripts. You were given, so you were provided, and that's going to be, remember, your mole A is what's given, 5 moles of carbonate. So you've given 5 moles CO3. And what you need, or mole B, is going to be mole of calcium. So to set it up, you're going to take your 5 mole carbonate and put it where mole A is. So if you want to follow along, go ahead and take this sheet that we wrote with the mole ratio setup and just kind of put it below so you can follow along. So mole A given, given mole A was 5 moles carbonate. So we put the 5 moles of carbonate where mole A would go. Then you can go ahead and set up your mole ratio, because the next step is mole ratio. And the mole ratio is from your balanced compound. So we're looking at our balanced compound of CaCO3, and mole B goes on top. Well, CO3 is mole A, so that would go on bottom. Mole B is Ca. So we look at Ca. There's no subscript with Ca, which means there's 1 mole of Ca. So we put 1 mole Ca2 plus on top. And then we look at mole A, which is CO3. CO3 does have the subscript 3, but remember CO3 is also a polyatomic. So there's just one of them, otherwise it would be in parentheses. So we do put 1 mole CO3 2 minus on the bottom. And another easy check to see if you've set it up right is mole CO3, the units cancel out, so you have set it up right. Then you have to solve. So 5 times 1 is 5, as you always multiply across, divided by 1 is still 5. So you end up with 5 mole of calcium ions. Okay, let's try another sample problem. Given the compound magnesium silicate, how many moles of magnesium ions are present if there are 12 moles of silicate ions provided? Okay, let's walk through how to solve this. So the compound we were given was magnesium silicate. We were told we have 12 moles of silicate. So mole A, remember, is what we're given, so that's 12 moles of SiO44 minus. Remember, silicate's SiO44 minus. Mole B, is what we're looking for, and that's magnesium. Then you can pull this over, this mole ratio setup, because remember, our setups are going to be really similar, if not the same. They're very formulaic. So mole A goes over here to the left. So we were given 12 mole silicate, so 12 mole silicate goes to the left. Then we're looking for moles of magnesium. So that's our B. So we can go ahead and build this mole ratio from our balanced compound. So mole B on top, we look at mole B. Mole B is magnesium. There's a 2 next to the magnesium. That means there's 2 moles of magnesium ions. So we write 2 mole Mg2 plus. Mole A goes on bottom, that is silicate, SiO4. Silicate is a polyatomic, not in parentheses, which means we have 1 mole of silicate. So we have 1 mole SiO4 minus. Now I can double check. Mole silicate, they cross out, so I can solve 12 times 2 is 24, divided by 1 leaves me with 24 mole of magnesium. That is my answer. Okay, let's do problem solver 3. Given the compound silver 1 nitrate. That's not the right problem solver. Sorry. Given the compound iron 3 sulfate, how many moles of iron 3 ions are present if there are 16 moles of sulfate iron provided? Okay, let's walk through. You were given a balanced compound of iron 3 sulfate. you were given 16 moles of sulfate, and they want to know how many moles of iron 3. Now, we can look at sulfate here and see that it's SO4, so sulfate's a polyatomic. It's in parentheses with a 3 next to it. So we know that we're going to have more than one sulfate, and we already have 2 irons. So our mole ratio is going to be not a 1-to-1 or a 2-to-1 ratio. It's going to be an uneven ratio. So mole A always goes to the left. So we were given 16 mole of sulfate, SO4 2 minus. And then we're converting that into mole B, which is iron. So mole A from your balanced compound goes on the bottom. So mole A sulfate has 3, so I have 3 mole sulfate. And mole B from your balanced compound always goes on top. That's 2 moles of iron. And then you can solve for your mole B. Now remember, this is when I talk about the ratio or the way you solve being really important. You multiply across and then divide down. So 16 times 2 is 32. 32 divided by 3 gives you about 10.67 moles of iron 3. And please remember, although we don't usually, well, we never will have uneven moles in a mole ratio, you can have uneven moles going in and partial moles coming out because you're determining how much you actually need to have 16 moles of sulfate.